Okay, so if you, the learner, have ever found yourself just drowning in information, like you've got 10 browser tabs open, maybe 3 PDFs you know are important, a spreadsheet somewhere, and, I don't know, a half-finished notebook.
Oh, yeah. Been there.
Right. And you're trying to pull all that into one clear answer. The problem isn't finding info. We're swimming in it. It's the plumbing, right? How do you connect it all reliably?
That exact mess, that operational headache, is what today's source material tackles. We're looking at Tongyi DeepResearch. It's presented as an AI research agent.
An agent, okay.
Yeah, specifically built to fix that plumbing problem. The idea is automating web research, at scale, but crucially, giving you a result you can actually trace back. Citations, the whole deal.
Gotcha. So our job here is to really dig into the material we have, the paper, the specs, and figure out what makes this thing tick.
Yeah.
What makes it a focused tool for long horizon, deep information seeking.
And how does it manage to be efficient, but also transparent enough that you'd actually, trust its output?
Exactly. Which brings us to that term you used, agentic. What actually separates an agentic AI like this from, say, a standard large language model? Because lots of LLMs can give you answers.
That's the fundamental question, isn't it? Most LLMs, they respond. You give them a prompt, they give you text back, they're reactive. An agentic system, it acts. It's not just predicting the next word for a report.
Yeah.
Deep research runs this continuous loop. Think, act, observe.
Think, act, observe. Right.
So in research terms, it holds a plan in its working memory. It calls out to tools. We'll get into those specific tools to gather actual evidence. And here's the key part. If the evidence comes back and contradicts its current idea, it adjusts.
So it course corrects based on what it finds.
Precisely. It changes its hypothesis, updates its plan. That loop is how it makes steady, reliable progress on those really complex, multi-step questions where you need, proper due diligence.
Okay, that makes sense. Let's unpack the architecture then. Because doing that kind of rigorous research, especially with AI, often hits a wall with, cost and speed. The source material mentions it's open source code, paper, weights all public. That's great for transparency. But what about the tech underneath? How does it stay fast enough for these long jobs?
This is where it gets really interesting from an efficiency angle. Deep research uses what's called a mixture of experts backbone.
Mixture experts.
Yeah, think of it less like one huge monolithic brain and more like a big consulting firm with lots of specialists. The model itself has a huge potential knowledge base, 30.5 billion parameters in total.
Whoa, okay, that's big.
It is. But, and this is the clever part, for any single step, any single token it processes, it only activates a small fraction of those experts, roughly 3.3 billion parameters.
Wait, hang on. So you get the reach, the knowledge scope of a 30 billion parameter model. But for most operations, you're only dealing with the computational cost and latency of about 3 billion.
You got it.
That sounds incredibly useful if you're worried about compute budgets.
Exactly. It's a core design choice for this kind of work. If you need to run long, complex research tasks repeatedly, stuff that might take a person hours, that MOE structure keeps the throughput high, and the cost, relatively speaking, manageable. Efficiency is sort of baked in.
Okay, that covers the speed. But how do they train it to be responsible? You said it's trained for agency, not just conversation. How do you teach an AI to do research with actual rigor?
Yeah, it wasn't just standard training. The sources describe a 3-phase process. First, something called agentic mid-training. That's where they specifically built in the planning and the memory management skills.
Right, the core agent parts.
Then, standard supervised fine-tuning, SFT. That basically teaches it the mechanics, like how to correctly call the tools it has access to. Gives it a good starting point.
Okay.
But the third step sounds like the real kicker, strictly on-policy reinforcement learning, RL.
On-policy RL, what does that add compared to other RL methods?
It sharpens the agent's behavior based on whether the final answer is actually correct and well-supported, not just whether it, sounds plausible or follows the right format. They essentially trained it to see the research process itself as a challenge to solve, pushing it to develop better strategies for maximizing factual accuracy in its final output.
Interesting. So it's rewarded for getting the right answer backed by evidence.
That's the goal. And to get that evidence, it needs to interact with the world. It needs tools. Let's focus on the 5 core tools mentioned. These seem to be what turns it from just a language model into something that can check its own work.
Yeah, this is the practical toolkit. It's all about external validation. First up is search. Pretty standard. Uses a web search API to get a list of potential sources.
Okay, basic web search.
Then there's visit. This one's important. It's described as a targeted page reader.
Targeted. How so? It means the agent doesn't just ingest an entire messy web page. It tells the visit tool, go to this URL and pull out the content relevant to this specific question. It helps avoid overwhelming the context window.
Ah, I see. The source mentioned services like Gina are often used for this. Why need a special tool like that? Can't the model just, browse?
Good question. Reliability, mostly. Dedicated page parsing tools are just better at handling things like dynamic JavaScript content, sometimes navigating cookie banners or paywalls where it's allowed, of course, and stripping out all the website Chrome, the ads, the menus. They deliver cleaner text for the agent to work with.
Okay, cleaner input. Makes sense.
Yeah.
What else is in the toolbox?
We've got a Python interpreter, essential for any kind of calculation, running quick data checks, maybe even simple plots. It's the analytical piece.
Right, for the numbers.
Then Google Scholar Access, really important for academic research, tracking down papers, following citation trails, adds that layer of scholarly validation. And finally, a file parser. This lets it read local files. You provide documents, maybe spreadsheets, other media, and turn them into text it can understand. Ties everything together.
So those 5, search, visit, Python, Scholar, file parser. Those are the levers it pulls to check his own reasoning against the real world and your local data.
Exactly. They turn the internal thought process into verifiable actions.
Okay, that gives us a good picture of the internals. Now let's talk setup. How does someone actually start using this? The sources mentioned a couple of paths.
Right. The easiest on-ramp is usually the hosted demos. They mention Hugging Face or ModelScope having online versions you can try out.
Play around with it first.
Yeah. And if you want to use it programmatically, like call it from your own code, but without setting up the whole model locally, you can apparently access it via OpenRouter. The name listed is Alibaba Tongyi DeepResearch 30B-A3B.
Okay, hosted options. But what about the power user? Someone who wants to run the whole agent locally, have full control.
That's definitely possible, but it takes more setup. You need a clean Python 3.NU environment, clone the repository. But here's the catch. The tools aren't free.
Ah, right. The external access.
To run it locally, you absolutely must provide your own API keys for the tools it needs to function. Specifically, the docs mention needing a Superkeyed for the web search component.
Okay.
And Janapa keys for that crucial page parsing visit functionality we talked about.
So even though the core model from Alibaba is open source, actually using it to interact with the web requires setting up and paying for these third-party commercial services. That's a key dependency.
Definitely something to be aware of. It's like having the car engine, the LLM, but needing to buy the gasoline, the API access separately.
Which brings us neatly to the hardware question. That 30 billion parameter number sounds substantial. Can you run this thing on a typical desktop PC with a decent graphics card?
The sources are pretty upfront about this. The full unquantized 30B model, generally no. It needs server-class VRAM. Think A100s or similar. It's not really built for your average gaming rig.
Okay, reality check. So what's the workaround for someone with more modest hardware?
There is one. If you're experimenting or developing, you can run the tool stack locally, manage your API keys, the Python interpreter, etc., but configure the agent's logic to call out to a hosted endpoint for the actual LLM inference.
Ah, so you split the load.
Yeah.
Keep the orchestration local, but use a remote brain for the heavy lifting.
Exactly. It separates the big compute part from the tool coordination, lets you manage costs and complexity a bit better, especially early on.
Makes sense.
And speaking of costs, the sources suggest a couple of practical tips for when you're starting out. Cache your search results so you don't keep hitting the API for the same query, and use exponential backoff on your API calls to handle rate limits gracefully.
Smart. Okay, so once you have it technically running, what's the advice for actually integrating it into a workflow in a way that builds trust? You can't just flip a switch, right?
No, definitely not. The suggested path is start small, start narrow, pick one specific recurring research task, maybe like tracking competitor press releases each week.
Okay, a defined use case.
Then write a simple one-page spec. What tools is it allowed to use? What's its budget? Maybe an API calls. What does success look like? But the most critical part.
Let me guess.
Logging.
You got it. Log every single tool call. What did it search for? What page did it visit? What was the result? What was its reasoning? And then you review those logs regularly, maybe weekly. That builds the audit trail.
That chain of custody, yeah, that seems essential to go from just playing with it to actually relying on it. Okay, let's shift gears and look at the quantitative data provided in the sources, the tables. Benchmarks aren't everything, we know that, but they do give us some solid ground for comparison.
Agreed, they're a useful map. Let's start with the core specifications table. Pretty straightforward facts here. Model type, Agentic LLM with MOE, as we discussed.
Right.
Context length, a hefty 128K tokens. That's crucial for holding on to information during those long, multi-step research processes.
Yeah, 128p is pretty big, allows for a lot of evidence gathering. And it highlights two main inference modes, the standard React mode and something called heavy mode, which seems to be for when you need higher confidence.
We'll come back to heavy mode. Let's look at the benchmark scores table first, specifically the AVG at 3 scores. Scanning these numbers, you start to see a pattern, don't you, where it really shines and where it finds things tougher.
Definitely. It posts really high scores on benchmarks that seem focused on retrieval and synthesis across multiple documents. Look at frames at 90.6, Xbench DeepSearch at 75.0, WebWalker QA at 72.2.
What do those benchmarks typically measure?
They often involve tasks like finding specific facts scattered across several provided documents or web pages, and then combining them accurately into an answer. Multi-hop reasoning, verifiable retrieval. This agent seems to be very, very good at that, a real retrieval specialist.
But then you look at other scores and it paints a different picture. Humanities last exam is much lower, 32.9. Browse comp is 43.4. These seem like different kinds of challenges.
Exactly. Those benchmarks often involve more ambiguity, maybe more complex reasoning, tasks that are less about just finding and stitching facts and more about, well, deeper understanding or judgment. It shows the boundaries. It's an excellent finder and combiner of verifiable information.
But maybe not a great philosopher.
That's a good way to put it. These lower scores give us a realistic expectation. Human oversight is still critical for those more nuanced tasks.
Which brings us back to heavy mode. The spec table mentioned it, and the benchmark table sometimes shows scores with heavy mode. How does it try to boost performance on those tougher benchmarks?
Right. Heavy mode is basically the agent investing more compute time when you need higher certainty. The sources explain that when you turn it on, it doesn't just do one research attempt.
Okay.
It runs several parallel research rollouts. Imagine asking 3 different researchers to tackle the same hard question independently.
Oh, like parallel processing for research.
Sort of. Each of these parallel runs or trajectories gets summarized into its own compact report. Then there's a final step where the agent takes all these different reports and synthesizes them into one consolidated, hopefully more robust, final answer, all still happening within that big 128K context window.
That sounds like it would use significantly more resources.
Oh, certainly. But you see the potential benefit in the scores. Like you mentioned, humanities last exam jumps from 32.9 in standard mode up to 38.3 when heavy mode is applied. It's a trade-off. More cost for potentially higher accuracy and reduced uncertainty on difficult problems.
A calculated trade-off.
Yeah.
Makes sense. And just to briefly touch on the context provided in the sources, the origin.
Right. The material notes it was developed by Tongyi Lab at Alibaba AI, and importantly, it's been released openly, Apache 2.0 style license.
Which is significant, right?
Yeah.
Having a capable open source research agent out there.
Absolutely. It increases access, provides competition, allows for community inspection and improvement. It's a positive development for the field overall.
Okay, let's wrap up by talking about risk. Because when you have an AI agent actively going out, hitting APIs, reading web pages, doing complex reasoning, things can go wrong.
Yeah.
The sources actually categorize the expected failure modes.
Yeah, they anticipate issues. First category is just practical problems.
Yep.
Tool failures. An API is down, you get rate limited. The mitigation there is standard engineering, implement retries, maybe have fallback tools.
Okay, operational stuff.
Second is grounding errors. This is where the agent misunderstands the information it retrieved. Maybe it misreads a number in a table or cites a source that's actually slightly off topic. The fix there involves better prompting, maybe stricter constraints on how it uses the tools.
Makes sense. And the third failure mode, this one sounds trickier. Synthesis drift.
Yeah, this is potentially the most subtle and dangerous.
Yeah.
It's where the agent takes a set of carefully gathered, maybe nuanced findings, and in the process of writing the final summary, it either overstates the certainty or maybe smooths over important caveats.
Turning careful research into a potentially misleadingly confident statement.
Exactly. It drifts away from the grounded evidence during the final synthesis step.
So how do you mitigate that?
Accountability through verification. The suggestion is to add a mandatory final step, a short verification pass. Before finalizing the report, the agent has to reread its key citations and rerun any calculations it performed.
Double-checking its own work.
Right. And if it finds a sentence in its draft report that isn't directly supported by the evidence it just rechecked, it has to flag that sentence for human review. The core idea, as the sources put it, is to make the agent behave like a careful assistant, not a confident storyteller.
I like that framing. A careful assistant. That feels like the right operational goal. Okay, so pulling this all together from our look at the sources, Tongyi DeepResearch seems designed to tackle that initial research bottleneck head-on. It uses its toolkit to read widely. It has mechanisms like MoE for efficiency. It tries to check its own work, and it can even ramp up its effort with heavy mode if you need more certainty. And crucially, it's open and inspectable. It seems like a tool built for getting actual work done.
Yeah, it looks like a serious attempt at building a practical research workhorse. So if you're listening and thinking about trying this, here's the final thought, the challenge maybe. Don't just play with it in a sandbox.
Okay.
Wire it into one single real process you have right now. Pick a report you currently generate manually, something that takes human time this week. Give the agent a clear task and a budget, maybe time or API calls to produce its version.
And the crucial next step.
Compare. Compare its final answer directly against what your human process produced. But don't stop there. Go back to those logs we talked about. Look at every action the agent took, every search, every page visit, every calculation it ran via the Python tool. Compare that process to how a human would have done it and to your own expectations.
So compare the output and the journey it took to get there.
Exactly. That act of direct comparative use, moving past just curiosity, that's what will show you exactly where this tool shines, where it struggles, and where it genuinely earns its keep in your actual day-to-day operations. That detailed comparison is how you build real trust.